Good afternoon, good morning, everybody, and welcome to the Green Roads webinar series. My name is Rebecca Stapleton, and I will be moderating today's session. I'm a senior transport specialist here at ADB and one of the team members of the Green Roads Toolkit. The Green Roads webinar series discusses cross-cutting dimensions on decarbonisation, climate resilience, water management, biodiversity, disaster risk reduction, construction materials, and inclusive growth for developing green roads. These webinars are anchored in the ADB Green Roads Toolkit and assessment tool. And before we do get started, I'd just like to remind everyone that all of our past webinars and presentations are uploaded to the Development Asia website for Green Roads, and we will share the link to this site in the chat box. And today's webinar will focus on the topic of low carbon concrete for walkways and pathways. But before we get into that, we need to go through our house rules. So please remember that we should keep our microphones muted at all times. And for questions which may come up during the presentations, we would like to encourage you to please place those questions into the Q&A box. And at the end of the presentations, we have allocated about 15 minutes to go through those questions. Our next webinar will be held on the 24th of April, and the topic will be biodiversity and roads. The webinar speaker for that session will be Gordon Keller, and Gordon was one of the authors of the Green Roads Toolkit and assessment tool, so that one should also be quite interesting. And now, what you're all here for. Moving to today's webinar, we will hear from two speakers, and we'll have, as I mentioned, approximately 15 minutes for Q&A at the end of the presentation. Our speakers will be Alex Campbell, Director of Engineering at Anyway Solutions, whose expertise centers around pavement engineering, pavement asset management, and climate resiliency. And we'll also hear from Zeev Halber, who has been the CEO of Anyway Solutions since its inception in 1999. So without further ado, I will hand over to Zeev. Thank you.
Thank you very much, Rebecca. Alex, if we can upload the presentation. Good morning, good evening, good afternoon, good night, wherever you are on the globe. It's a pleasure to be introduced, and thank you for the ADB for giving us the opportunity to present another cutting-edge technology from Anyway Solutions. And today with me, co-presenter Alex Campbell, Director of Engineering. Thank you, Alex. We can continue. So Anyway Solutions is a climate resiliency focused consulting firm with over 20 years of experience, part of a much larger group of companies with over 70 years of global business experience. And we're proud to have a multicultural, multinational team of experts, and we've been providing solutions and designs that are focused on climate resiliency for over 25 years. So much before climate resiliency and climate change has been recognized as a significant thing for the world, we've already been there, and we've been dealing mainly in developing nations. And as I said, over the years, we are proud to be a company that does not only hold our heads up in the sky in I would say space, using cutting edge satellite, AI, machine learning technologies, but also have our foot on the ground, dealing with practical solutions that the industry of infrastructure is so much needing. So starting from 1998, already there, we developed a technology that is aimed at stabilization, soil stabilization for pavement structures. We already then looked at lowering the content of cement and lime being the what was then considered as traditional stabilizers. So we've expanded the research and actually uh, developed a patented technology for stabilization, then moved on to additional fields of infrastructure building, looking at low-cost housing and developed technologies for low-cost housing. Again, lowering carbon emission that, instead of concrete, let's localize solutions, uh, look for much lower carbon emission as part of construction, things and technologies that fit well with the developing world, further developed earth-based plasters, and then mineral paints. And now we've come to 2024, where we actually were patented for a low carbon emission concrete. So as you can see, right from inception, the company is very much technological, yet very practical in the technologies and solutions that we present and offer to the industries wherever they are. Continue, Alex. So I'm not to talk too much about how much concrete is involved in the developing of the world, the construction, the amount of um, cubic meters of concrete per person is mind-boggling. With concrete comes cement, and cement, as we all know, unfortunately contributes as much as 8% of carbon emissions in the current world, and we all understand the consequences and how much it is important to lower such emissions. Um, Only in the United States, not talking about many other parts of the world, the use of concrete has significant contribution to creating carbon emissions, and it is something that the world and the industry is recognizing as being very important to tackle, to deal with, and to actually lower. And so it is important to come with more comprehensive approaches, innovative solutions to actually be able to lower carbon emissions from uh, concrete and cement and concrete industries. We can move on, Alex. The industry, as we all know, has taken action, and many of the leading companies in the world, I would say conglomerates, that deal with cement and concrete together have put in place um, an ambitious plan and have set goals to actually achieve carbon neutrality across the industry by 2050. So although it looks very far in the horizon, it's not actually very far. And many of the leading companies of the industries, Holcim, Heidelberg, they all started developing and looking at how to actually lower carbon emissions. And they actually look at the complete value chain of creating concrete in terms of how do they plan to actually tackle that. This actually what has led us, thank you, Alex. This is actually what has led us in looking at the what do we want to develop here? What is the technology that we think that actually could be useful and could actually meet almost all these goals and targets that the industry has put to itself? If you look at this diagram, then if you would notice on the right-hand side, you can see those elements that the industry actually holds as those that will contribute to achieving the goal of carbon neutrality by 2050. And so 50% of the actions and the elements that they're looking at are efficiency of design and construction, and production of concrete and the elements that are involved in concrete, savings or changing cements and binders, which actually contribute, as I said, and we all know, quite a lot of carbon emission into the concretes that are being used in the world. And of course, trying to save on the clinker production. So these 52% are those parts and elements that we focused on. The other parts actually relates more to the energy that is being used in the production of cement and carbon capture, decarbonation technologies and techniques that are also out there, but this has not been what we have thought as something that we can contribute to. It's not based on our expertise and experience, and so we looked at the other side of the equation. Alex, we can continue. And the industry, as I said, is looking at the complete value chain. So looking at the clinker, minimizing the use of clinker, maybe addressing different cements, the concrete itself, the construction and the implementation of concretes is very much important in playing a role in lowering the carbon emissions of the use of concretes. And as I said, carbonation is the other side of the equation. So there are actually 7 goals that the industry has put to itself to achieve. And I can proudly say those who are in bold are at least 4 of the 7 goals that were set are met, and we were able to achieve through the development of this unique patented technology of low carbon emission concrete, replacing raw materials and use recycled materials, produce low carbon cement mixes, and optimize the lowest life cycle emissions, looking at the application itself, and introduce new cement mixes. So we've looked at as always, we took a practical yet a comprehensive approach to developing a technology that we believe can contribute a lot to lowering carbon emissions for the industry. Our traditional interest has always been in transport infrastructure, and so the first take we took is deal with walkways and pathways, and that's what we've created, a low carbon emission concrete for walkways and passes, and we actually call it pathway. We can continue, Alex. This is actually quite a may look as a puzzling diagram, one that actually presents the on one hand the embodied energy that relates to production of different materials and the embodied carbon dioxide emissions in each materials, and I've looked at it many times. Alex, maybe you can pitch in and give the audience and myself maybe what should we make out of this?
Sure, thank you. And it's a well-circulated diagram. It's about 15 years old, and we can talk about the actual accuracy of the embodied CO2 and embodied energy. But at the end of the day, what this diagram is trying to show you is, the impact of our industrial processes or materials that we're using and that impact on the environment. But really, if you look at concrete and we're talking about how impactful that is on our environment, yet it's quite low on this graph, what we need to remember is that's the concrete component. If we're looking at reinforced concrete, we have steel that contributes to that. We have various aggregates. But also the take-home message here is the amount of concrete that we have. So while it might be lower on this position on the graph, the amount of concrete that we're producing and that we're using globally contributes significantly to the impacts of our environment.
Thank you, Alex. So it is about the quantities. And so it's unbelievable how much concrete we use. And that's the approach that we took. We took an approach that actually looked at the materials, looked at the implementation of a solution, the what we call fit for purpose solution, one that will be following the same practicalities and production means that are known to the industry, not trying to be difficult, actually follow what the industry already knows, other than maybe introducing, not maybe introducing, patented, innovative materials and an approach which Alex will provide much details about in the coming slides. So as I said, we've decided to deal with materials, with application, and it is all based on our vast experience in bringing in technologies that are practical, easy to apply, and may significantly contribute to the protection of the environment, lowering of carbon emissions, and that has been a major motivation for our company for many, many years. And this technology that we are presenting today is only a continuation of that. So Alex, I will now transfer the stage to you.
Great.
Go on.
Thank you, Zeev, and thank you everybody for being here. Good morning from a very cold and dark Canada. Good evening, good night, wherever you are in the world. I looked at the list of attendees and can see a lot of familiar names, not all of them colleagues and friends, but those who are contributing to the Green Roads movement globally. So thank you for making the time. For me, this is interesting. It's a little bit of full circle. You know, when I started out as a young engineer, I was working with understanding the chemistry of the reactions associated with fly ashes on mines in South Africa. And, you know, since then, I've been traveling the world working on various low volume road projects. I'm thrilled to see that Gordon is the next speaker. So please make sure that you sign up for that. He's a great speaker, great visuals, and I've had the luxury of being able to work with Gordon both personally as well as on some other projects. So this, you know, the way that we've developed here is from the experiences we've had, as Zeev had mentioned, through understanding the chemistry of soils and hydraulic materials, as well as the impacts that we see of using a lot of these, you know, highly impactful materials like concrete. And those of you in the Philippines, for example, with the majority of your roads being rigid systems rather than flexible systems, you can see the impact of concrete, you know, all the way down to the South Pacific, where I work a lot, where there's a lot of thin concrete pavements for low volume roads. So concrete is and cement is an integral part of our industry, but what we try to look at and the problem we try to address is to solve, you know, to produce a reduced carbon or low emission strength, low strength concrete for the construction of, you know, potentially low volume roads, walkways, pathways, not significant structural materials that you use in bridges or buildings, but addressing what we know best, and that is transportation, use of soils, use of waste recycled materials. And we want to use that to reduce firstly, the quantity of cement that's used in the mix, to use ingredients that are recycled from quarry waste, for example. We wanted to include other ingredients that were recycled from a carbon sink standpoint to reduce the footprint, by eliminating the need to both use reinforced steel in some circumstances. In others around the world, we use plastic sheets as a membrane to try and reduce the reliance on that, and come up with a technology that could be both patented as well as applicable to the sort of fit for purpose approach we're talking about. So Pathway uses recycled raw materials, so I'll go into how we got to that process. It's optimized design, so we're talking about what I call fit for purpose, right? Creating a solution that is fit for a problem, right? And trying to use recycled materials, reduce cement contents for the low volume road pathway environment. And also, reduce that low carbon cement mix design. So what we did is we assessed really various mix designs in the lab. We played around a lot with just our understanding of hydraulic materials, and played around in the lab, but also in the field. And we did a lot of work. Sometimes you need to fail to succeed, and went through lots of different mix designs, lots of different gradations of materials, different recycled materials, all that to say that we came up with a combination that worked very, very well, at which point we applied for a patent, which was received. A lot of people said that, you won't receive that patent because, what are you doing that the big conglomerates around the world don't know already, but lo and behold, here we are. So what we're doing right now is we're undergoing refined testing at UC Davis. So we've got a package of results that we've done in-house as well as some other labs, but now we're doing that sort of refined assessment of how good the product is, how can we push some limits? Can we increase the strength so that we could use it potentially in other applications? So that's the process that we're undergoing right now. So our solution and benefits, essentially Pathway, this is just a picture on the right of one of the trials that we were doing. We use a monofilament fiber, and we found that using a monofilament fiber in our mix design decreases the amount of shrinkage cracking. So it produces longer lasting pavements using local materials. But it was also important to meet international accessibility standards. So if we are using it for pathways or walkways or low volume roads, a lot of times those paths or walkways are going to be used by people with disabilities. So it's very important for us to pass the various, the scrutiny of accessibility standards. It may not necessarily be something that is becoming, well, certainly for ADB it is, but certainly in North America, the Accessibilities Act is becoming something that is gaining significant amount of momentum. So that was really one of the touch points we needed to solve, is that it needed to meet these accessibility standards for walkways and paths. So there's less than 2% in the mix design. We incorporate a lot of it is ground granulated or GGBFS or slag as we commonly know as a pozzolan, and a pozzolan is important hydraulically because it provides density in the design or in the hydration process, but also contributes to long-term strength. I won't necessarily go into the technicalities of the benefits of a pozzolan, but other pozzolans include fly ash, for example, slag, silica fume, rice, corn, husk ash. But really it's a material that by itself doesn't react, but in the presence of calcium, i.e. from cement and or lime, reacts to form strength gaining properties. We want to use recycled quarry waste. And that was something that was important to us because through our contacts, we were always asked by various quarries, whether it was a borrow pit or for a specific project, there's always this material that can't be used, particularly in a road, but also in concrete. It's typically too fine. It's fine. Fine modulus is too great, which isn't fantastic for hydraulic materials because it tends to lead towards cracking, and cracking in a road, a path, is what we're trying to avoid. So it was important for us to take a look at that waste material and say, okay, how can we use this material to create something usable, therefore, decreasing the footprint not only of the quarry, but also the footprint of the material that we are creating. So in essence, really, like any hydraulic material, we're using waste quarry aggregates, a hydraulic binder. By hydraulic binder, when we talk about that, hydraulic means you add water, it starts to react, strength gaining properties occur, and you're left with a semi-rigid or rigid slab. Paramount to the success of any hydraulic binder is the addition of moisture or water, right? You can't start a reaction without water. Cement in a bag or just sits there waiting for water to hit it, and when it does, the reaction starts. It was also important to try and decrease the time of curing, and so we looked at trying to accelerate or decrease the amount of time that required from placement to opening up to have load-bearing properties. And so essentially what this created was what we're calling Pathway, which was an environmental alternative to concrete with high durability and ease of application. That was what we were trying to achieve. So when we first got to the quarry, we tried various materials, and typically quarry dust, depending on the geological source, tends to be limestone based. A lot of the building materials used in projects are limestone based. That doesn't mean that the pathway system can't be used with materials that aren't of a limestone base, but the ones that we've looked at, and a lot of the quarry waste globally tends to be limestone based. But it was important to, not only just from a chemistry of limestone, but also, more importantly, the fineness of the material. So the fineness of the material is something that is outside of the window that we typically use for concrete. So an aggregate that would be used in concrete would be somewhere in between well, for those of you that aren't colorblind, the green and the purple line, or the one with triangles or X's. And the typical gradation that we used from our quarry waste products is the blue line with the squares in it. And you can see that there's no way this material would be permissible to be used within a concrete system. It's, has a much lower much lower large particle size fraction and a much larger smaller particle size fraction. And it's that smaller particle size fraction that typically gives issues related to shrinkage cracking. And you want that larger particle fraction to give it substance and load-bearing properties. So it was a very challenging material to work with, but one that we needed to find a solution for. Did a lot of chemical analyses, associated with using X-ray diffraction. I'm not going to go into what this is, but essentially we're just understanding, the mineralogy of the materials that we're working with. And then from the mineralogy of the materials we're working with, taking a look at what does our mix design or our hydraulic material look like prior to it being added, to the aggregate or the matrix. And then understanding through doing a bunch of different tests, understanding, okay, what does that look like, before hydration and after hydration? And, we talk about hydraulic materials, so calcium is the backbone of hydraulic reactions. Really, the basis for that is the calcium Firstly, because of its association with hydroxide, increases the pH significantly, and that pH can help to open up reaction sites on aggregates. Certainly in clay materials, calcium fits perfectly into the interlayer spaces. So calcium is one of these magical elements when it comes to hydraulic chemistry. So we also, went into trying to understand, slump and things of that nature, right? Slump is essentially, how workable the resultant mix design is. Does it flow too much? Does it not flow enough? And when you're using fine materials, it can be extremely complicated to have on the one side the material flow too much, and then on the other side not flow at all. And that's referred to as called a thixotropic material, one that the boundary between where it flows and doesn't flow is very, very tight. And so it's important for us to really understand, how does addition of water affect not only the strength we're getting, but then the applicability in the field. And that's something that Zeev will chat about in a little bit, of the trials and tribulations we had in applying the product. So a lot of our testing obviously revolved around strength of both cores taken from projects that we've undertaken, but also, perfect system cores that you would cast in a laboratory to understand, how different aggregate mixes or how different applications of binder would impact or change the strength of that resultant pathway that we're creating. So a lot of that work, has been done. It's continuing to be refined in the laboratory right now to try and manipulate how we can push the boundaries of strength, but also prevent the amount of cracking that would occur by increasing either a dosage or changing the matrix that we're working with. A lot of the shrinkage cracking I've been mentioning, if we took a look at, okay, with our mix design, if we typically applied, it would be cement to our mix design, how would that react? And that was important for us to understand. And on the left, you can see here, we have a shrinkage cracks that were developed. This is a specific test to understand shrinkage. You can see how cement applied to the matrix, the waste aggregate produced cracking. And then, with the refined mix design that we created, there is no cracking. So that means that what we have created reacts with this material much better and doesn't produce the same sort of shrinkage cracking as you would expect if you added OPC to that same mix design. And a lot of that comes around, is based on, firstly, the changes in chemistry that we've applied to that mix design, but also the inclusion of monofilament fibers. So fibers, for me, the best way to describe it is it makes that linkage between the micro and the macro. So it creates stability within a system that prevents, that shrinkage from occurring. And that can be of great benefit in the field where you won't get that same degree of cracking or issues in a project. A lot of the testing we did was pretty rudimentary, as I mentioned before, looking at, wheelchair accessibility. This was not necessarily for that purpose, although we have done testing, which I'll get to, but we wanted to see, what would it look like from a rutting standpoint if we loaded not just a car, right? Because cars have a different contact point between the tire and the road, but something aggressive like a highly loaded wheelchair or, a bike that would have a very high PSI tire. So there's a greater stress on that road. And so we ran the wheelchair that was loaded to simulate sort of an 80-kilogram individual, over 1,000 times, and tried to see if we could get our system to rut. And while it isn't necessarily as scientific as you could do in a lab with some sort of wheel, which we have since done as well. But just a way of us trying to understand the system that we have and how it can contribute, from a durability and a strength standpoint. Skid resistance is important. We talk about that not only for vehicles, but for wheelchairs. So if you test a material for skid resistance of a wheelchair, essentially you're looking to have better skid resistance, also for walking, right? You don't want to have a slippery surface. And so the best rating you can have is like an R13 rating. So ours was well above an R13 rating. And essentially what you're looking at is changing the angle of a surface to a point where a specific load starts to slip on that surface. And so the greater that angle without that specific load slipping means that the friction factor is better, i.e. The skid resistance is better. So very, very good skid resistance, which is good for use in paths and things of that nature. So we look about the calculated embodied carbon emission. So what we're trying to do here is come up with a way of assessing embodied carbon emission. And this is one of the key projects we have at UC Davis, is to really refine, what are those values, to get an unbiased assessment of what is that embodied carbon content. And what we've discovered so far is that, creating a walkway of a similar thickness to a typical green or low emission thin concrete, we would have a lower embodied carbon content. And that was the objective of the assignment, was to try and create something that had a much lower embodied carbon emission. If it had a higher embodied carbon emission and yet the same strength, means that we didn't create something that was worthwhile. So this was critical for us in creating a system that could be used fit for purpose. Again, we're not using this to construct a bridge, to build a high-rise. We're using this fit for purpose, low volume roads potentially, pathways, walkways, where we don't need to necessarily have that super high rigid concrete slab when there could be an alternative that will serve the same purpose. So lastly, before I hand it back over to Zeev, so some of the technical information, we've used quarry waste, and we use a quarry waste with a fineness modulus of less than 3.1. So really what that's telling us is, we want to, we're using material that would not be permissible using a traditional, OPC or slag OPC blend. Right, calcium driven is important, and also the inclusion of industrial waste materials, i.e. quarry waste or quarry dust and quarry aggregates that wouldn't be able to be used outside of what we're using them for. There are mountains and mountains, or megatons of waste quarry aggregate that's just stockpiled that isn't used. And so there's a large opportunity to utilize that material for the benefit of Mother Earth. We really try to eliminate the need of a plastic sheet either at the interface between the aggregate and the slab, but also to do without metal reinforcement in the slab. That's not always traditional in sidewalks. It depends on the region, the climate, and the purpose. But to create a system that wouldn't use rebar was important for us. Fast curing times, or at least curing times that were not greater, were important so that we could have that solution trafficked or used much faster. As far as international standards for what we're looking at is strength, durability, skid resistance. We are complying with skid resistance and strength for use in sidewalks and in slabs. And we're also looking to embed that carbon emission, right? So we're reducing it significantly compared to using, an OPC or OPC slag or OPC pozzolanic blend, of that same thickness or for that same application. So what we've tried to create and what we've been successful in creating is a use of waste quarry aggregates that can be used using hydraulic chemistry that we've developed over the past sort of 25 years, and our understanding of the needs of a lot of the countries where we do work, i.e., a different way of installing either pathways, walkways, or low volume roads, or other elements associated with a developing economy. And so with that, I'm going to pass it over to Zeev, who'll talk more about the more interesting part is the application, the look, the feel, some of the issues we've overcome, and the type of product and solution that we've created.
Thank you, Alex. I'm always fascinated about everything that we've been able to achieve. So again, leading us as a company, and also within this, with the development of this technology, minimizing the footprint of every technological solution that we've developed as a company, localize the solutions, follow industrial practices, and actually come with a faster, maybe more efficient construction methods, ones that will not actually be very different than what the industry or the sector is used for. And because while the industry has actually targeted, not always contractors or people who actually implement solutions are open to that. We want to share a few short, seeing is believing. So maybe go back, Alex, one. Let's go one slide back. So as you can see, yeah, this one. As you can see, the concrete, as you can see, the concrete is placed directly on compacted aggregates. Just one forward, Alex, please. It is being applied with no rebar, no metal, no plastic sheets under it or membranes. Oops. Yeah, I wanted to run a short video, Alex.
It's running on my side. It might not be buffering to the Zoom call.
Oh, okay. So well, how do I run this one?
I'm running
so
it.
you can so you can run the central part. The central image is a short video, not this one, the previous one. Yeah, run this one. Yes.
I am running it. It's not buffering.
Okay. Yeah. Oh, okay. So yeah, I mean, okay, maybe the videos are a bit too heavy, but as you could see, it's easy. In this application, in this project, we actually used the concrete pumps. The concrete was brought to the site with the concrete mixers and was then poured onto the surface, the compacted surface directly, and then leveled. So it's again following what the industry or the sector would look for. You can move on, Alex. And then leveled with, again, the same methods of applications, the same methods of building. This one was more of a more smooth surface. You can move on, Alex. And this is a video, and when you'll get the materials, you'll be able to see how smooth it is, how creamy it is. And I think this is the contribution of, again, using more lime, more lime in the mix, and less concrete. On the left-hand side is the finished. In the center, you can see how it was cured. And on the right-hand side, this is a 4-year-old slab. So you can understand the simplicity and how good it is in all terms, and how much it actually achieves all the goals that were set by the industry for developing low carbon emissions in the cement and concrete industry. We can move on, Alex. So just to touch base on these few projects that we already did, because it's very important for us to implement things really ourselves, put our boots on the ground and put our feet into the concrete. And so this is an example of a project we did with the Tel Aviv municipality, an observatory garden that is in Jaffa, looking over the old Jaffa port. We can move on. In all of these projects, we actually produced the concrete and brought it onto the site for a contractor to actually implement that. So it was very important for us to also learn through the process what are the limitations, what are we doing wrong, what is better. Just examples of real projects that are there and are serving the communities where they have been implemented over the past few years. Some of them are already 4 years old. So we've taken our time to, as Alex described, play around with materials, work in our own laboratory, then taking it out to outside laboratories, run through standard institutes like in Israel to actually see that we qualify for the required standards. And we're now taking another step towards looking at the limitations of our patented low carbon emission concrete technology, to see what else we can do and how much we can expand the boundaries with the UC Davis in the United States. As we said right from the beginning, this is based on a lot of experience, knowledge, and know-how, and trying to be practical in what we bring as a solution to the world, to our clients, to where we do business and where we are involved. We can move on, Alex. Just to say that low carbon emission concrete is possible. It's not something that is an imagination. You know, what was once imagined is now reality, and it can be achieved through working scientifically, practically, use a lot of knowledge and experience, and bring those solutions and technologies to the world, and actually be able to lower carbon emissions, because that is extremely important. On the other side of the equation, we actually work in bringing designs to tackle the consequences of climate change. So lowering carbon emission on one side, tackling the climate change consequences on the other end. These are the things that actually motivate us as a company and should motivate many other industrial stakeholders, wherever they are, whether they are private companies, consulting firms, or governments, if we actually want to save our world. It was a pleasure. Thank you very much. Thank you for giving us, ADB, the platform to actually present a practical, innovative solution for low carbon emission concrete. We are here to take your questions.
Excellent. Thank you very, very much. There are quite a few questions in the chat box, but so I'm going to start with one right from the bottom, because it was relevant to the last slides you were showing with the large slabs. So there was a question around if there's any effects of leaving out expansion joints in these mass concrete.
Me or you?
Alex, you want to answer that because that was part of our learning curve. Yeah, please go ahead.
Absolutely. Yeah, it's a good question. Absolutely, and we do put expansion joints in. We spent a lot of time trying to get around expansion joints, and just from trying to change the the way that the application and the curing of that application goes. But I mean, Mother Nature is Mother Nature. So we now have expansion joints. It's important, even though you don't get a lot of shrinkage or associated with hydration. It is a living entity that is hydrating. So to have it will crack where it wants to crack. So if we're putting expansion joints in, we're telling it where it needs to crack or where it should crack. So yeah, it's been effective. And as soon as we move towards placement of expansion joints, then yeah, there were no issues after that.
Okay, and I'm going to ask one more and then I'm going to hand over to my colleague. So there is a question here from Gordon Keller about if you've tried any test sections on low volume roads or possibly using it as a filler inside geocells.
Zeev, you want me to take that or you want?
Yeah, sure. I mean, we can both answer that. Very nice question, Gordon. Thank you very much for being up so late for us. Hope to see you soon. Certainly, we'll come and see your webinar next time. We intentionally we didn't start with low volume roads, and so we did not actually use that as a low volume road kind of application. Having said that, in all of the applications, eventually vehicles came onto the site. And so whether it was light vehicles or like what is, electric bikes, motorcycles, and even heavy trucks that had to be there and had to go on that slab in order to do some work next to it, uh, it was surprisingly nice to see that the slabs actually stood up to these factors that came in that they were not designed for. Certainly, we are looking at, as I said, in UC Davis, we will be looking towards expanding the use of this product to additional uses, such as in geocells for slope stability, sometimes in open drainage systems that are being used specifically in heavy rain scenarios, then yes, that will be the next phase. We did not try that yet, but that is part of what we are taking the technology towards.
Alex, you're muted.
I'm now unmuted. Thanks. Yeah, thanks, Gordon, for that question. Yeah, just so that's a lot of the work we're going to be doing with Samaya at UC Davis is and potentially a test track is to take a look at coming back to my low volume roads roots, the impact it might have on a low volume road, and also understanding that repetitive loading piece and to see how we can then design it and put it into designs for a low volume road outside of a rigid slab for a path or a walkway. So yeah, good question. It's something we're working on.
I'm conscious of time. We have a lot of questions and not a lot of time. So just going to combine these ones here from Lloyd. So one is about if you have mixed in colored powders in the mix, because oftentimes if we're doing a cycleway, we color the pavements. The other one is if anybody, for example, in our projects want to apply pathway, well, how does it work? So do you license the patent to local users?
I can answer the color one really quickly. Yeah, I mean, we've looked at in our development in the past, we've looked at changing the color just by changing the mineralogy of the of the fine material, essentially, of the clay. Like, so every aggregate has a slightly different color, whether it's in wherever you work, it's slightly different. So it would adopt that color. Yeah, we have looked at changing the color for architectural purposes. We get a lot of inquiries from architects saying, can you make it this color, that color? It's not difficult. Pigmentation reacts really well with it. So Zeev, you can answer the other one.
Yeah, well, this technology has been developed not for us to actually yet to actually be the seller of the technology of the concrete itself. We're actually looking to engage and collaborate with major global industry leaders to use them as the platform to make an impact. Because if we, as a small company consulting firm, will try to actually make an impact, that will not work. But if someone like, as an example, Holcim will decide to actually take on this technology and actually bring it out to the world, that will have an impact. And that's the direction that we will be looking at as soon as everything will be ready. That then you could actually be looking to buy this technology or this type of low carbon emission concrete at your local concrete supplier, coming out soon, hopefully.
Okay. One more from the chat box, and then I'm going to hand over to Ian. Oh, I've lost it. There it is. From Aldrin. Hi, Alex. Just asking what would be the advantage of this product over polymer liquid soil stabilizer, which is approved in his country.
Yeah, that's a long answer. I'm not going to get into liquid polymers and my just completely different. Liquid polymers. I'm not going politically. I'm not going to get into it. I'm not a fan of liquid based products. I find them finicky to use. Yeah, different horses for different courses.
Good answer. Okay, Ian, please come in.
Thanks, gentlemen. Sorry I couldn't say hello just before the session started. Just going back to really picking up on Gordon's theme there, and I'm actually out on a Pacific island at the moment. And when we get out onto the remote islands, we've often got coral aggregate. How does it react, or do you have any experience with, what I'd call salty aggregates, that or even indeed mixing it with salt water?
Yeah, God, you sound like Gordon. And Gordon's asked me that question so many times about using corals and stabilizing corals, and yeah, I mean they're tricky, right? The whole salt component aside, or the brackish water side. Yeah, look, from a stabilization standpoint, which is not too dissimilar to this, but looked at using salt water. A lot of it will depend on how brackish that water is. We've had a lot of success stabilizing or reacting with coral-based materials. Haven't tried it with this mix design yet, but understand the predicament that the South Pacific is in trying to use some of those materials. So it's not really an answer, but no, haven't looked at it yet, but would happy to look at it.
Sort of a follow-on theme, I guess. Again, how sensitive is the results to getting the mix exactly right at the start? Again, outer island, often hand mixed in a in a mixing bowl sort of thing. Do you have to get it? If you're off by a bit, does it all fall apart on you, or is there a bit of forgiveness?
Well, I would say there's a tremendous amount of forgiveness. I mean, I'll let Zeev answer that, but just through the experience we've had with, when you're starting sort of product development and you're getting your hands dirty, not using low tech more than high tech. Yeah, amazingly resilient with respect to differences in, moisture content specifically. Having been involved in low volume road projects in, South Africa, where you're, taking a bucket of this and a bucket of that, adding them together in a, wheelbarrow and putting it on site, it has to be flexible, right, in terms of its application procedure. Yeah, we've messed up so many times with our applications during the trial phase and still got good results. So I mean, Zeev can talk to it, but I'd say that it's pretty flexible. Yeah.
It's what we like to call a forgiving treatment.
Yeah,
So,
yeah, right, exactly. Yeah.
I'm really sorry, but I
so
am gonna have to cut you off
okay.
because we are at
Okay.
time.
Oh,
However, I note that we still have quite a lot of questions that are unanswered in the chat box, so we'll do our best to note these down and try and get responses included with the materials that we upload for this webinar session. When we upload it to the Dev Asia website. So perhaps, Mark, before we sign off, could you please just share that website again for everybody, so that everyone who's joined us today knows where to go to find those materials after today's session. I'd just like to thank again our two panelists today for what was a really engaging discussion. And thank you very much for being part of this Green Webinars series. Just a reminder as well to everyone again to please join us for the next session that will be on the 24th of April. And if you do have time, we do have a survey about today's session. Mark or Chris, if you could just put up that slide so those that are still online can scan the QR or the okay, there we go. The evaluation form link is also in the chat box. So yeah, so that's it from us. Please join us again on the 24th. And if you have time, please do fill in this webinar sheet. So thank you, Zeev and Alex. Thank you.
Thanks, Rebecca.
thank you very much, Rebecca. Thank you.
Thank you. Bye-bye.